In this video, we will be looking at exponential functions. So naturally, the place to start is, well, what is an exponential function? The exponential function f with base a is denoted by f of x is equal to a times b to the x power. We're going to restrict that b to be positive, so greater than 0, and not equal to 1. And then x can be any real number. In the expression 2 to the third power equals 8, we call 2 the base and 3 the exponent. So in our exponential function, b is our base and x is our exponent. So what makes this an exponential function is our variable x is in the exponent. Something that we'll see along the way is if our b value is greater than 1, then our function is going to be growing as x increases, so we call that exponential growth. And if our b value is between 0 and 1, so something like 1/2 or 1/3 or 1/12, then the function is going to be decaying as x increases, so we call that exponential decay. We're just going to start by evaluating some exponential functions just to kind of get the feel of them. So we evaluate exponential functions just like every other function. We're just going to substitute in the value of x for the x in the function and see what we get. So for f of 3, we're going to plug in 3 for x. So that will be 2 to the third power, and 2 to the third power is 8. So f of 3 is equal to 8. For f of 1, that would be 2 to the first power, and that's just 2. F of negative 5, that's going to be 2 to the negative 5 power. There are a couple ways we can attack this. First of all, we can say, well, we know how to handle negative exponents. Put it in the denominator. This is 1 over 2 to the 5th power. That simplifies to 1 over 32. That's fine and dandy. That makes me happy. Life is good. If you want to check your answer, you can type it in your calculator. 2 to the negative 5th power, decimal. But you should have somewhere on your calculator a way to change decimals into fractions. For mine, I have to hit math, enter, enter, and it tells me it's 1/32. If you don't know how to change decimals to fractions, let me know, and I'll help you figure it out. For f of 0, I'm going to plug in 0 for my exponent, so I have 2 to the 0. And one of our rules is if we have 0 for an exponent, then it's simply just 1. F of 0 is equal to 1. We're going to continue evaluating these exponential expressions, just looking at some a little bit more complicated. This time our function f of x is going to be 5 times 3 raised to the x plus 1 power. And we want to find f of 2. So that means I'm going to have 5 times 3 raised to the 2 plus 1 power. When I simplify this, I'm going to have to make sure that I follow the order of operations. So first is parentheses. The only parentheses I have are surrounding 3, and I can't simplify just a 3. It sits there. Next up is exponents. In my exponent, I have a 2 plus 1, and I can simplify 2 plus 1. That's going to be 3. So I have 5 times 3 raised to the third power. I need to simplify my exponent. 3 to the third, that's 27. So I have 5 times 27, which is 135. If you're nervous, your calculator will do the order of operations for you. You just have to know how to type it in. We have 5 times 3 raised to the, in parentheses, I'll have 2 plus 1. And that gives me 135 as well. So your calculator is smart enough to do the order of operations. So if you're worried, type it in. It'll be okay. Next up, we're looking at f of 0, which will give us 5 times 3 raised to the 0 plus 1, which is 5 times 3 to the first. The 3 to the first power is just 3. So we're getting 5 times 3, which is 15. Being able to evaluate these functions is going to be huge because it's going to help us when we are graphing them. So make sure you're understanding where these values are coming from. There's one more exponential function we need to look at, and it's a very special kind. It's called the natural exponential function. It's going to use the number e. Yes, the number e. Kind of like how pi is irrational, and it's about equal to 3.14159. E is kind of the same idea. In some exponential functions, an irrational number is used for a base. This number is e. It is approximately equal to 2.718281828. You need to find the e button on your calculator. It might look like e to the x. It might look like e to the square. It might look like e to the y. It might just look like a lowercase e, but you need to find that lowercase e. You also might have e caret. So find that button on your calculator, and you're going to need to know how to use it. So e is called the natural base, and we call f of x equals e to the x the natural exponential function. We're going to practice using this e button because it is going to be really, really useful. So first up, we want to find f of -3 if our function is f of x equals 7e to the x. So just like before, I'm plugging in this number for x. So I'll have 7e to the -3rd power. On my calculator, that will look like 7. My e button is second natural log. And that gives me the e to the caret. And I want to raise this to the -3rd power. I'm going to round out to 4 decimal places. We're going to do that a lot this chapter, or this unit. So I'm looking at about 0.3485. For f of -1, that will be 7e to the -1 power. So 7e to the -1 is about equal to 2.5752. F of 0 is equal to 7. Well, wait a minute, this one's a lot nicer. I don't get this weirdo decimal, so what's going on? Remember, anything raised to the 0 power, except for 0, is equal to 1. So really what I'm doing is 7 times 1, which is 7. That's why it's turning out so nice. Finally, f of 1 will be 7e to the 1st. And 7e to the 1st power is about equal to 19.0280. So right now we're just rounding out to 4 decimal places, getting an idea and a feel for how to use this e button, practicing using it. So make sure you can find that. Now that we've evaluated some of these functions, we're going to work on graphing them. So we're going to start by graphing 2 to the x power. This is going to give us a lot of information about exponential functions in general. So we're given the function f of x is equal to 2 to the x. We're going to complete a table. Because if you ever do not know how to graph something, you can make a t-chart or a table, figure out what values you get, plug in the points, and you will get an idea for what your graph is supposed to look like. So for example, if we're looking at y equals 2 to the x, and x is equal to -3, then that will be 2 to the -3rd power, which is 1/8. If I plug in -2 for x, 2 to the -2, that's 1/4. 2 to the -1, that's 1/2. 2 to the 0 is 1. 2 to the 1st is 2. 2 squared is 4. 2 cubed is 8. Now remember, each row on this chart is giving me an ordered pair that I can plot. So -3, 1/8. That's going to be a point on my graph. So I find -3, 1/8, that's going to be about here. -2, 1/4, about there. -1, 1/2. 0, 1. 1, 2. 2, 4. 3, 8. And I think we're starting to get an idea of what this graph is going to look like. If I play connect the dots with a nice smooth curve, on this side it's pretty easy. You just know it's going to kind of swoop up forever. We just have to know what's going on this side. Well, if I were to keep going, I'd plug in more and more negative numbers. So I'd get 2 to the negative 4th, 2 to the negative 5th, 2 to the negative 6th. That's never going to turn negative. I'm going to get really, really close to 0, but it's never going to go negative. So what it's going to do is it's going to kind of flatten out here. It's going to look like it sits on the x-axis, but it's really never going to touch. It's just going to get really, really close. We're going to answer some questions about this graph. So I'm going to be flipping back and forth a little bit. Not sure why it printed twice, but we're only going to answer the questions once. So we want to find the domain, the range, the y-intercept, the horizontal asymptote, and decide whether this is growth or decay. So let's start with domain and range. So remember, to find the domain of a graph, we are looking at what x values it touches. This arrow says we're going to the left forever. This arrow has us going to the right forever. So our domain is going to be all real numbers. We're going to touch every x at one point or another. For the range, we're thinking about y values. While we hit all the way up to positive infinity, the question is how low do we go? That's where it becomes really important about what we talked about on this side. We're going to get really, really close to y equals 0, but we're never going to touch it. There's no value you can plug in for x and get 0 out. So what that means is that our domain is negative infinity to positive infinity. Range. We're going to get really, really close to 0, but we're not going to touch it. To say we don't touch it, we use parentheses. And then we go up to infinity. If we were able to touch 0, we'd use a bracket, but we can't. Y-intercept, that's where we cross the y-axis. That would be right here. And that's going to be at x equals 0, y equals 1. Horizontal asymptote. A horizontal asymptote is a horizontal line that you get really, really close to, but you don't quite touch, for the most part. Technically, that's not the definition, but that's how we tend to think about it. Well, hey, we said we were going to get really, really close to 0, and we weren't going to touch it. So that horizontal line is going to be our horizontal asymptote. But it's a line. Lines have equations. So I need the full equation for this horizontal line. Think Vuxhoy. We are looking at a horizontal line. Horizontal lines have 0 slope. Their equations are y equals a number. In this case, we're getting really, really close to y equals 0. So that's going to be our horizontal asymptote. Finally, we want to know whether this is growth or decay. So I want you to think back to when we were talking about increasing and decreasing. We go from left to right. If we go up, it's increasing. If we go down, it's decreasing. From left to right, we're going up, so we're increasing, and we would call that exponential growth. The other way we can think about that is by looking at our base. Our base in this case is 2. We said that if our base is greater than 1, then it will be growth. And if it's between 0 and 1, it will be decay. Since it's greater than 1, it's growth. We're going to take a look at another example of this just to see what different graphs we can get out. So the next one we're going to look at is g of x is equal to 1/2 raised to the x power. We're going to graph this one the same way by just plugging in some x values, plotting some points, and see what we get out. So first up, we'll plug in x equals -3. 1/2 raised to the -3 power. It's going to be 8. but just to check, 1/2 raised to the negative 3, that's 8. That may surprise you, but if we think back to our exponent rules, we can figure out why this is true. 1/2 raised to the negative 3 power. Because it's a fraction, we can put that negative power on our numerator and denominator. So 1 to the negative 3 over 2 to the negative 3. We said if we have negative exponents, they can turn positive if we switch what side of the fraction bar we're on. So that'll be 2 to the positive 3 over 1 to the positive 3, which is 8 over 1, which is 8. That's just kind of one way to think about it. 1/2 to the negative 2, that'll be 4. 1/2 to the negative 1 is 2. 1/2 to the 0 is 1. And we get 1/2, 1/4, 1/8. So this is kind of backwards of the one we just did. Let's see what the graph looks like. Negative 3, 8. Negative 2, 4. Negative 1, 2. 0, 1. 1, 1/2. 2, 1/4, 3, 1/8. So it really does look like the last one, just kind of flipped. So if we use our smooth curve, just like last time, we're going to get really, really close to that x-axis, but we're not quite going to cross it. And we're going to work on the same questions about this one. I'm going to go ahead and copy over the graph just so we can have it on this side. So we had negative 3, 8, negative 2, 4, negative 1, 2, 0, 1, 1, 1/2, 2, 1/4, 3, 1/8. So first up is the domain. The domain is the x values we're going to touch. Just like last time, we're going to go negative infinity to positive infinity. So in general, when we're dealing with exponential functions, our domain will be all real numbers, negative infinity to positive infinity. That is not the case for the range. For the range, we need to figure out which y values we're restricted to. Just like last time, we're going to get really close to 0, but not quite touch it. So that will be 0 with parentheses. And we're going up towards infinity. Our y-intercept, x equals 0, y equals 1. Our horizontal asymptote, still y equals 0. But this time it is decay because as we go from left to right, we're going down. And just like we said, if we look at our b value, that base, it is between 0 and 1 this time, which just emphasizes the fact that this is decay. So we can see it both algebraically and from the graph that this is decay. Now you might be asking yourself, when I get to my open math, how am I supposed to graph this? Because it's really picky about graphing. Well, you are in some serious luck. The way you graph these exponential functions on my open math is by plotting the vertical intercept and one other point, and it'll fill in the rest for you. We have to know what a vertical intercept is first. Vertical intercept, that'll be the intercept on your vertical axis. That's our y-axis. So what we need is the y-intercept and one other point. If we click those 2 points in order, then it will fill in the graph for us. So first up, we need the y-intercept. The y-intercept is where we touch the y-axis. Everywhere on the y-axis has an x value of 0, so we need to plug in x equals 0. If you ever need a y-intercept, plug in x equals 0. That goes for every graph ever. So if I plug in x equals 0, I'll get y equals 3 times 2 raised to the 0 power. But 2 to the 0 power is 1. So this is 3 times 1, which is 3. When x equals 0, y equals 3. That's it right there. We need another point. We can use any x value we want. It's totally up to you what you use. I try to use something close to my y-intercept so that I'm fairly certain it'll land on the graph. I like to use x equals 1 because it's a nice number. If I plug in x equals 1, then I'm going to have y is equal to 3 times 2 to the first power, which is 3 times 2, which is 6. So if I plot that, then I'll have 1 comma 6, which will be right here, and my open math will do the rest for you. It will look something sort of like this, and something like that. So when you're graphing on my open math, you only need to plot the 2 points and it'll plot the rest for you. So I have said time and time again, and I will continue to say, that if you ever don't know how to graph something, then you can use a T-chart and it will work. That is true. But I'm going to show you another way to look at this that might save you some time. You can graph with transformations. We saw this a little bit before, but I just want to show you what it looks like with exponential functions. So we're going to start with the graph y equals 2 to the x. That's going to be kind of our parent function. It's our starting place. If we add 5 at the very end, that's going to shift the graph up 5 units. If we subtract 5 at the end, that's going to move the whole graph down 5 units. If we add or subtract from the x, meaning we're in the exponent, remember that's going to be a horizontal shift, but it's backwards of what you would expect. So a plus 3 is actually going to move us to the left 3, and a minus 3 is going to move us to the right 3. If we put the minus out front, so if we throw in a negative out front, then that's going to flip us in the y direction, which is flipping over the x-axis. And if we put the negative in front of our x, that's going to flip us in the x direction, which is over the y-axis. So I'm going to keep this graph that we just did out for a second, because I want to reference it for this next problem. It says to graph y equals 3 times 2 to the x minus 2 by graphing y equals 3 times 2 to the x and applying the transformation. I'm not actually going to graph it here. I'm going to graph it on the other one. So now we want to graph y equals 3 times 2 to the x minus 2. Well, according to those little rules about graphing with transformation, this minus 2 is going to shift us down 2 units. So whatever points I have, I'm going to move them down by 2. And it will look something like that. So knowing these transformations can be really helpful because it can just set up your graph really nice. We're going to practice a little bit more because these ones are a little bit confusing in the beginning. We're going to graph y equals negative 2 raised to the x power and y equals 2 raised to the x plus 1 power. I'm going to start with the basic function for these, the parent function, y equals 2 to the x, and then we'll figure out what these transformations do. We already graphed y equals 2 to the x today. 4, 8. It looks something like this, and then it kind of levels off. So let's start with y equals negative 2 raised to the x power. The negative isn't attached to my x, so I think of my negative as being attached to my y. If the negative is attached to my y, then I'm flipping in the y direction, so I'm flipping vertically. So this is going to be called a vertical reflection. It just means I'm going to flip or reflect over the x-axis. In other words, I'm taking all of my y values and making them negative, or changing the sign. So if I flip this over, it's going to look something like that. Can you see that reflection over the x-axis? That was a little bit easier than trying to graph the function by finding all the different points. Let's see if the other one works this way. We're doing y equals 2 raised to the x plus 1. The plus 1 is attached to my x, so I know I'm shifting in the x direction. I just have to know which way. Since it is in the x direction, we know it's backwards of what we think. Plus 1 would make us think we're moving to the right, but it's backwards, so we're going to shift our original graph to the left one. So we're taking 2 to the x and moving it to the left one. So every point that I know of, I can shift to the left 1 unit, and that will give me this graph. I don't want to mess up my markers, but it's going to line up pretty well with the back one as you get down because they get really close together. But it's still shifting that entire graph to the left 1 unit. Again, we could have made a t-chart. We could have filled in the values. There's nothing wrong with that, and I will never tell you that you can't. I just want you to see this other way so that you have an idea of just another way to think about it. Now that we've looked at some exponential functions, we're going to try to write some of our own. And the way we're going to write these is by using the formula f of x equals a times b to the x. If we are in this form, there are multiple forms, but we're going to use this one for now. We can think of b, our base, as 1 plus r, where r is our rate of change. If our b value is 1, then we're not changing because we're multiplying our value by 1. So that r is going to tell us how much we're increasing by or how much we're decreasing by. It doesn't say it here, but just so you know, a is our initial value, and it always will be. So for example, if we have an initial value of 101, and we want to have a growth rate of 14%, our function will be f of x is equal to, first we have our initial value, 101, times b we said is 1 plus r. So I want to take 1 plus, our growth rate is 14%. But we don't want it as a percent. When we deal with it in math, we deal with it in decimal form. So 14% is 0.14, and that's going to be raised to the x power. So I'm just following this example. And if I simplify that, I'm looking at f of x is equal to 101 times 1.0, oh geez. Try this again. F of x is equal to 101 times 1.14 raised to the x power. Next up, our initial value is 86, and we have a growth rate of 3%. So we'll have f of x is equal to, our initial value is 86. In parentheses, I'm going to have 1 plus 0.03. So that'll be 1.03. To the x power. Next up, we're going to have a growth rate of 113%. Let's think about that for a second. This as a decimal is 1.13. So when I do my b value, I'm going to have to take 1 plus 1.13. So that means my function is going to be f of x is equal to 65 times 1 plus 1.13 is 2.13. And that'll be raised to the x power. But then we see this decay rate of 9%. How do you think that's going to change things? Well, decay means we're decreasing. So our R value in this case is going to be 0.09, but because it's decaying, it's going to be negative. So when I set up my function, I'll have f of x is equal to, my initial value is 119. In parentheses, I'm going to have 1 minus 0.09. That'll be raised to the x. So that's going to simplify to is 119 times 0.91 raised to the x. This is going to be decay because my b value is between 0 and 1. So we see that that's how that decay rate comes in. We have to be especially careful on this last one, where we have a decay rate of 0.8%, because our R value in this case is going to be a negative 0.008. So be careful with your zeros. So when I write my function, that's going to turn into f of x equals, my initial value is 125. If I do 1 plus a negative 0.008, it's going to turn into 0.992, and that's raised to the x power. So whatever rate you're working with, you're going to add it to 1, and that's going to give you your b value. We're going to try to work with one of these exponential models. The equation y equals 901 times 1.032 raised to the t models the number of students in a certain state that go to out-of-state colleges and universities each year from 1996 through 2003. Where y is the number of students that study out of state, and t is the number of years after 1996. Assuming this equation remains valid in the future, we want to estimate the number of students that studied out of state in 2010 and the number of students that will study out of state in 2023. Try to find that key piece of information that's trying to trip you up. T is the number of years after 1996. So to figure out what I'm plugging in for T, I need to figure out how many years have passed since 1996. One way to do that is subtract subtract 1996 from my year. So 2010 minus 1996 gives us 14. So in this first example, we're going to use t equals 14 to find the number of students that studied out of state in 2010. So y is equal to 901 times 1.032 raised to the 14th power, and my calculator can help me with that. I'm going to round nearest person because that only makes sense. I'm getting 1,400, and that would be students. So in the year 2010, assuming this model is still valid, 1,400 students studied out of state. Now we can try the same for finding the number of students that will study out of state in 2023. So we can take 2023 minus 1996, and that'll tell us how many years have passed. That'll be 27. So if we plug in t equals 27, then we'll have y is equal to 901 times 1.032 raised to the 27th power. Which if I round to the nearest student, oh, it's really darn close anyway, 2,109. And again, that's measuring students. So make sure you're reading your questions and you know what your variables mean. That's the biggest part of application problems in general, is being able to understand what information they're giving you and what they're asking. So in this case, they gave us a formula telling us that y was the number of students and t was the number of years after 1996. In both parts of this, it was looking for a number of students, so we knew we were solving for y. And they gave us a year, which means they gave us the information we needed to figure out what our t value was. So really take your time to digest these problems and know what they're asking and how they're asking it. When it comes to exponential functions, it is pretty much a requirement to use compound interest. Compound interest is telling you how much interest is accruing on something if it is compounding a certain number of times per year. So compound interest is when a bank pays interest on both the principal, which is the original amount you put in, and the interest that has already been earned. So if you earn interest, then you get to earn interest on the interest. The formula for compound interest is A equals P times 1 plus R over N raised to the NT power. A is the amount it's worth now. P is the principal, the original amount you put in. R is your interest rate. We're going to write it as a decimal. N is the tricky one. It's the number of times that interest is compounded per year. So we're going to be looking at 4 different examples here for different values of N, and T is going to be our time in years. So they want to know if $14,300 is invested at an interest rate of 8% per year. Find the value of the investment at the end of 5 years for the following compound methods to the nearest cent. I'm going to start by dissecting this and figuring out what each of my variables are. I'm trying to find how much this is worth, so I'm trying to find my A value. P is my principal, and that's how much I put in originally. That was the $14,300. R is my interest rate as a decimal. This is 8%, so we're going to write it as 0.08. We're doing this for 5 years, so our T value is going to be 5. Finally, we need our N value, the number of times we're compounding per year. And that's going to be different for each of these parts. If something's happening annually, it means it's happening once per year. So for annually, our N value is 1. Semi-annually means twice per year, so N is 2. Monthly, well, there are 12 months in a year, so we'll use N equals 12. And daily are 365 days in a normal year, so we're going to use N equals 365. We're going to set up all these equations the exact same way. We're just going to change our N value each time. So how this is going to look is A is equal to 14,300 times 1 plus 0.08 over whatever N value we have, raised to the N times 5, which I can write as 5N. And then I can just plug in my different values of N. So let's see what we can do. 14,300 times 1 plus 0.08 divided by 1 raised to the 1 times 5. So that's going to be my annually amount. And it looks like I am getting $21,011. They wanted us to round to the nearest cent, so I will say in 39 cents. I now want to type in the same thing, but my N value is now 2 because I'm doing semi-annually. That's going to give me $21,167.49. Monthly, I need to switch out my N value for 12. And that's going to give me $21,304.79. And then for daily, I need to plug in 365 for my N. And that's getting me $21,332.16. So that's just plugging in my different values of N. And what it's doing is it's saying, how often am I going to check how much money you have total and figure out the interest from there? You might notice that as we compound more and more frequently, the amount of money we get is going up. So $21,011, $21,167, $21,304, $21,332, but the amount that we're increasing by is getting lower. So we had like $150 jump between annually and semi-annually. Between semi-annually and monthly, we jumped by like $130 some dollars. Between monthly and daily, we only jumped by $28. Well, what if we compounded twice daily, or 4 times daily, or 68 times daily? That number would keep increasing until we were just compounding all the time. And that's where we get to continuous compound interest. So if we legitimately were compounding all the time, how much would we make? We're going to use the exact same problem. We're going to do this with continuous compounding. So continuously compounding interest means your principal is constantly earning interest, and that interest keeps earning interest on the interest earned. The formula for this is A equals PE to the RT. Same A, same P, same R, same T. We're just going to use E, the number that we used earlier. So same numbers as before. Our P value is 14,300. Our R value is 8%, which is 0.08. Our T value is 5. So if I plug in my P, 14,300, times E raised to the 0.08 times 5. If this were to compound continuously, we would be up to $21,333.09. If you look back on what we did if this was compounding daily, this is less than $1 more. So the difference between daily and continuous isn't all that much, which is kind of interesting. This compound interest is something that you really need to look into if you're taking a loan or if you are putting money into an account. So this is real world stuff here. This is stuff you can figure out and actually use when you're out dealing with financial problems.